Hello students, welcome to Maths 1325 Applied Calculus, Lesson 1, Functions and their Graphs. Now, entire Lesson 1 is on review, but I strongly advise you to stay in for sections 1 and 2, which I marked essential. If you feel comfortable, then you can skip sections 3 and 4. If you feel really comfortable, that is. Okay, let's begin. Section 1, Functions. This is how we define function. Start from Cartesian product. So, or pair of numbers, x, y. And if there's any equality between x and y, we call it a relation. Here's some examples. Some relationship between x and y. This relation, by the way, will be a circle. And if you have 1, 0, then put it in there. 1 squared plus 0 squared is equal to 1, so this one works. Not surprisingly, this point, blue point, is right on this circle right here, 1, 0. However, if you put in 1, 1, plug those in there. 1 squared plus 1, that's 2, not 1. So this red point, 1, 1, is not on this circle. Here's another relation, x squared minus y squared is equal to 1. It turns out this hyperbola, again, we have a couple of examples on the curve versus not on the curve, which are determined by whether that 1, 0 or 0, 1 satisfies this relationship or not. Here's another relation, y equals x squared, but this one is rather special. This one is a function. The others are not functions, and we are going to discuss those shortly. Alright, now that we talked about Cartesian product and relations, let's talk about the domains and ranges of those relations. The domain is allowed x-coordinate values. The range is the allowed y-coordinate values. Want to see some examples? Here we go. If you have a circle, the domain is allowed x-coordinate, so as low as -1 to +1. Forget about y-coordinate, just look at the x-coordinate. Oops, I wanted to open this cell. So that's the domain. Now, the range, you have to look at the y-coordinate. Goes down to -1 down here and goes all the way up to +1. That's the range. In this particular case, domain and range are the same. By the way, you can visualize kind of like this. Horizontally, you have all those crossings. So horizontally, we go from -1 to +1. For ranges, you see, vertically, we go from -1 to +1. You can see all those crossings. That means we have valid points on this graph, on this relation. If you go all the way up there, then there's no crossing. That means the relation is invalid for anything. You can do the same thing for this one. Now, what's the domain and what's the range? The domain, well, allowed x-coordinate value. So this graph began from -3, but this curve will just go on forever. So -infinity all the way to -1, and then there's a gap. And then from 1 to +infinity. More specifically speaking, we are going to get something like this. Please note that we have to have closed bracket at -1 because this is part of the graph, and also at +1 because that's part of the graph. For the infinity, there are always parentheses because nothing is equal to infinity. You see, infinity is not a real number. Range, on the other hand, it goes on forever, -infinity to +infinity. You see, and move around, then you'll see y-coordinate is valid everywhere. There's no gap. X-coordinate, there's a gap here, but y-coordinate, there's no gap. You can visualize kind of like this. If you move around by these vertical lines, and as you can see, no crossings there. So there's a gap, and that gap is between -1 and +1, which is expanded out. For range, now if you move around all those y-coordinate by moving all these horizontal lines, then as you can see, we have no gap every time we have a crossing. So just we have negative infinity to infinity. Here in this picture only from -3 to +3, but you can easily see that the graph will extend further. Compare that with the previous graph. Stops, no more down here, no more up there, no more to the right, no more to the left. Third one is here. I'll leave this one to exercises for everybody. The answer key is posted here, so if you open up and you can see the answer. All right, we went through the concepts of relations, domains, and range. Now let's talk about functions, because the concept of domain and range is necessary to define a function. A function is a special relation where each x in the domain is related to one and only one y in the range. Previously, let's go to another general relationship here. For given x coordinate value, for example, at x equals to 1, you have only one point right here. But if you go to x equals to about 0.5 or x equals to 0 here, that's easier to see. Then I have two crossings. Y coordinate here, 1. Y coordinate down here, -1. So one person is related to two people, and that's not a function. So each married person must have one and only one spouse. That's a kind of analogy I can think of. And we have these kind of different notations for the functions. And if you feel a little bit lost about these notations, it's going to be okay for the most part. So please be warned. Pair notation. So you can express a function by pair, x comma y, x comma y. But if they're related the same way, then this y1 and y2 are the same. So here are some examples. Dark roast, $1. Light roast, $1. Cafe mocha, $3. Cappuccino, $3. That's a good menu. Yeah, you can see things like that. Cheese melt, $1. Nacho Supreme, $2. Bacon double, $3. Happy Meal, $5. Okay, and the price tag here is ridiculously small for today's standard. But you see, this is valid menu. And unlike here, where dark roast and light roast has the same price, and cafe mocha and cappuccino had the same price, here we have different price tag for every different items. So this is one of the examples of one-to-one function, and this is just not one-to-one, but it's a function. Now look at this one. Standard oil change, $30. High mileage oil change, $40. Full synthetic, $50. Full synthetic, $60. What is this? This is not a valid menu or a valid price tag here in this service. I mean, full synthetic is $50 or $60. Which is it? We have a problem. I mean, with coupon, maybe 50, or for limited amount of times, 50, but it's not specified here. It's not a function. Third one is not a function. So pair notation is one of those things that we can use for functions. We use it especially when we have this parenthesis, this pair notation, x comma y expression. So remember this. Another expression is arrow notation, input output. X is input and then output comes out. So same input goes in there, then same outputs come out. X goes in and then y1 comes out, or sometimes y2 come out and they're different, then this is not a function. They have to be the same. One and only one output is associated to the same input. Here's an example. Cheeseburger, McChicken, bacon double, and the price goes there. I mean, I got this from the textbook. And then activity level, this is an example of one-to-one function. And this one here, this is not a function. This 240 is associated to 12 or 20. Which is it? It's unclear, so it's not a function. This one's okay. Different items from the domain being assigned to the same output in the range, that's okay. But same item, one item from the domain is assigned to two different outputs, that's not right. So this is an arrow notation, and please remember this. So for some elements to element, we use this arrow with this, do you see this vertical bar here? And that's a proper notation, but if you forget about this vertical dot, this small line segment here, I'm not going to take off any point, but that's a bit more proper notation here. And if you assign set to set, then we use usual arrow without that vertical bar. See the difference here? From element to element, we use this vertical bar, and from set to set, we use just plain arrow. Getting a little bit intimidated? Well, sorry about that. I already warned you about these. Now, algebraic expression, that's something we are going to be using quite often, more often than the others. So we have y value expressed explicitly in terms of x. Now, this thing is very useful if you have some algebraic expression, but if you do not have algebraic expression like those price tests and stuff, you can't do it this way. But in this class, we'll do this a lot because we're going to rely heavily upon algebra. Examples are here. I mean, yes, here. So output is 2x squared minus 3x when x is input. So explicitly given like this. Okay, we went through the concept of functions and notations of function. And as for the notations, if you forget about all these in abstract expression, that's not going to kill you. If you understand, great. And am I going to keep using these? Yes, I will. So it's going to be better if you remember all those. But you don't really have to master everything all at the same time right now. So if you feel still uncomfortable, just move on, and eventually these things will sink in as you see these more and more often. Finally, let's discuss algebra of functions. Especially when we have functions between numbers, then we can do these kind of algebraic operations. Addition is addition, subtraction is subtraction, multiplication by coefficient, and adding those up. And subtraction too, because b can be set as negative. In general, all these define another function. Multiplication as well, just multiply this output. As for division, we need one special thing because we cannot divide by 0. Otherwise, everything is okay. Here's some examples of algebra functions. We have this function f of x and g of x, and then add them up. Yeah, okay, add them up. What do you get? And then simplify. Never mind. I decided not to simplify this. Subtract. Yeah, okay, subtract. And multiply. Do we need some simplification here? Foiling? I decided not to. Okay, just multiplication. And division is the same as multiplying the reciprocal. So here, flip it upside down. Here, which I highlighted in blue. Flip it upside down, which I highlighted in red. And division becomes multiplication. All right, so much for section 1. Let's meet again in section 2 in a separate video. Stay tuned.